Please welcome everybody, Loubna Ben Allal.
Hi, everyone. Thank you for the introduction, for the invitation. I did understand some words in German. There's a gap in between reading machine learning papers and actually training machine learning models. It's a bit like learning to code. You can read about it, but you only really become a good programmer when you start writing code yourself, at least for now. So if you've ever read machine learning papers where the experiments all made sense and seemed feasible, and then you try to reproduce them, but nothing worked, then you already know what I'm going to talk about today. This is the life of machine learning researchers. On the left is what gets published in papers, the final architecture choices, the data mixture, the hyperparameters, and the evaluations. Everything seems clean, and it seems like it's almost easy to get those results. You just need enough resources to be able to train those models. But this is actually what happens behind the scenes. When you sit down to try to train models, so many things can go wrong. It's far messier than what papers make it look like. You can have debugging sessions at 2 a.m. You can also have very noisy or broken evals that make no sense. You can also have hardware failures where your run just fails and you need to restart sometimes from the beginning. So there's many things that can go wrong, and these things usually don't make it into papers. Technical reports are really nice. They push the field forward. They make the results like reproducible. But the bad thing about them is that they don't cover everything. For many cases, it's because you have to submit it to a conference and there's a page limit, so you can't put everything. You can't tell like your life story about how you had to stay up all night to debug something. But this information is really valuable for someone who wants to know what it takes to train models. So this was our goal with the small training playbook. We wanted to bridge the gap that exists between research papers and production models, because we kind of had to learn that ourselves, and we trained a couple of models, and we realized that this information is really valuable. And maybe it's more valuable to publish a blog post, which is really long, than a very polished paper that will get like a good rating at a conference. So this is the playbook. You can go read it in this website at Hugging Face. So I work at Hugging Face, and I led the training of SmolLM 3, which is the third family of the SmolLM models. It's 3 billion, it's multilingual, it has hybrid reasoning, and was trained on 11 trillion tokens. So the pre-training took around a month, and the post-training another month. And it was a fully open model. We published everything from training data to model architecture to code. And as you can see, it sits in the Pareto frontier of the Qwen3 model, so it's a very good model for the size. And at Hugging Face, we worked on other models like StarCoder, SmolVLA, so not just for text, but also for vision. We do a lot of work also on data sets and evals. So this playbook is kind of the distillation of all of this knowledge that we've carried over 4 to 5 years of training models and curating data sets. I'm going to structure today's talk in 3 aspects. The first one is why train this model. The second one is, if you want to train a model, what model should you train in terms of architecture and data? And the third question we're going to answer is how to train this model efficiently. So the first and most important question is why. And a lot of people actually skip the why and just go to the what and the how. But I think the why is really important because it can save you a lot of resources. You should ask yourself, do you really need to be training a model from scratch? because training from scratch is very expensive. It's like resource intensive on the money front, but also on like the human front. So if you can have another solution that will get you to your goal more efficiently, you should take it. Maybe prompting is enough, or maybe fine-tuning, because there's a lot of open models out there. So you need to really have a good reason for training from scratch. And here's a decision tree that I think is useful to help you decide if you need to train a model from scratch. I think the question you should ask first is, can any existing models already solve your use case? And this can go either through prompting. Maybe if you craft a really good prompt, you can actually get the model to do what you want it to do. And this is basically like with agents. Now it's just like filling them a really good context and they execute the task. You don't need to fine tune them on your task. So for many use cases, if you prompt the models well, you'll probably get a good enough answer. If prompting really doesn't work because the model is maybe a bit far from the domain you want, maybe you want a legal advisor, but you have some internal data that you need the model to be trained on, then fine-tuning can be an answer. You could take an existing model, which is already really good at general tasks, and then fine-tune it on your data set. So by fine-tuning, I mean like a short training where you don't start from scratch. And now fine-tunings can actually be expensive. For example, there's what we call mid-training. It's like pre-training, but you don't start from scratch. So you could train on like many tokens, but you start from a model that was already trained, and the cost is still like less than pre-training. So if fine-tuning works, then great, you can stop there. And if fine-tuning also doesn't work for some reasons, maybe you want some models that will work on specific hardware, and to do that, you need to change something in the architecture. Obviously, if you need to change the architecture, then you need to train a new model. Or maybe you want to train the model on some new domain, like DNA. If you take existing open models, they're really not suitable for DNA. So you don't need a model that is trained from scratch unless you want to cover English as well. So there are some reasons to train from scratch. And in the playbook, we put them in these 4 categories. The first one is research. You have a research question that you want to answer, or a hypothesis you want to verify. For example, you invented this new optimizer and you want to see if this optimizer actually works for training models. Then you will need to train models from scratch to test that. That was, for example, the Mu1 optimizer, if you heard of it. They needed to train from scratch to show that it works. The second reason is production. Like I already said, maybe you want some models that will run on specific hardware, then that could justify training from scratch. The other reason is experience. You basically just want to have experience in training models, which is an important skill in today's AI field. But then if you want this experience, it should like lead you to one of the 3 use cases. You need experience because one day you want to train a model for production. The last reason is strategic open source, and this is one of the reasons we've trained and released models. It's that you see that there's a gap in open source that you can fill. For example, the DeepSeek models were open source, and it gave the DeepSeek models like a lot of a good reputation in the field. So they kind of use this open source to kind of reflect the image of the people who developed it. And also at Hugging Face, we also release models to help the community develop more open source models, which will end up on the platform. So that's another reason to train models from scratch. So let's suppose you already thought about the why and you have a good reason to train a model. Then the second question you should answer is, what should you train? There's so many architectures you could choose from, so many changes you could do, so many data sets. So it can be overwhelming if you don't sit down to think about what should you train. And I think that to answer the what, it also goes back to the why. Why do you want to train a model? Is it like to run it on device? Then maybe certain architectures are better than others. So in terms of architectures, the most popular ones are dense models, which are standard transformers. And then you have mixtures of experts, which are like dense models, except that you take the feed-forward neural network and you replace it with multiple experts. So MOEs have been really popular last year and this year for the reason that they are more compute efficient. For the same compute budget, if you train an MOE, it will have a lower loss and so better performance than if you train a dense model. And then there's the hybrid architecture. A hybrid architecture is basically a combination of state space models and the standard softmax attention. And these models are really good when you want a model that has very long context. For example, you want to feed it like a lot of pages and like a lot in the context, and you want it to support all of that. So hybrid models are useful for that. So how can you choose one architecture over the other? So dense models are the standard ones where you load all the model parameters into memory, and when you send this a query, all the parameters activate, and then you get your answer. MOEs are more interesting because when you send a question to the MOE, not all the parameters activate, only a fraction of the parameters activate. So you will get your answer faster because there's less parameters to run. So MOEs are more efficient during inference. But you still need to load all the model parameters in memory. So if you're really memory limited, MOEs are probably not the best choice. But if you're not memory constrained, MOEs are definitely the way to go, because you can have a model which is large, but during inference, it's like you're using a small model because you don't need to activate the whole network. And today, most of the releases have been mixtures of experts. So for you to decide, we also have this decision tree where you can ask yourself, am I memory constrained? If you're not, then you can ask yourself about your team's expertise. Dense models are definitely easier to train because this is the standard. They're very mature. MOEs are still kind of recent. I think today there's some libraries to train them like Megatron, but they're not as battle tested as the private libraries that these labs have, like for example, Meta or OpenAI. So I think they still require a team that has already trained models. If this is your first model training, maybe it's better to start with dense models. And then once you know how to train dense models, then you can go to mixtures of experts. And then for the hybrid models, they also require some experience and or maybe an open timeline to get them to work, because there's some mixed opinions about their efficiency. So what to train? The first step was basically choosing an architecture from dense, MOEs, or hybrid. There's other architectures like diffusion models, but I think for language models, they're not that mature, so we're not gonna cover them here. So step one is checked. Now step two. Okay, I want to train an MOE, but how many layers, how many attention heads? There's so many things to decide on. The answer is don't reinvent the wheel. Start from a baseline. Look for a model which uses the architecture you want to use and which has a model size like the model size you want to train. And then start from there and tweak it one by one until you get a model that you're satisfied with. So for example, here we have a table where we share some good base models for dense and for MOEs and for hybrid. And they all come in like different model sizes. So it's very likely that you will find the model that is close to the one you want to train here, and then just start from it as a baseline. So step two is covered. Now step three. I have my architecture, I have my baseline, but I don't want to train the same model as this baseline. I want to do some changes because there's many things that go into a transformer, and maybe if you change some things, they will make the performance better or the inference better or the memory better. And there's many things you can change. They're like doorknobs, but you shouldn't change everything. This is like my one advice. Don't try to tweak everything. Like usually when you have someone who's junior, they're like, I'm gonna change everything, like try different layers, try many things, but I think it's just a waste of time because the baseline is already battle tested. Whoever trained that, if it's coming from a big AI lab, there's a reason they chose like this architecture. And you should only change the things that will get you closer to your goal. For example, for us, when we're training SmolLM, we wanted a small model that will run on device. So we wanted the really fast inference. So if there was one thing we could change to make the inference faster, we should change it. So for example, attention, when we talk about this, there's multiple options. There's like multi-query attention, grouped query attention, and there's one that is more efficient than the others. So we did try the efficient one, like we changed it and we saw if that works better. And another thing we wanted in our model was very long context. So for us, we started from a llama baseline, and we're thinking, what things can we change in this architecture to make the model better at long context? So we read a lot of papers, and we found that there was this thing called hybrid NOPE, where you basically change the positional encoding, and the model is supposed to become better at long context. So that is one thing we changed. But there were some other things that we didn't change, for example, like the initialization. Once you have decided what things you want to change in the architecture, you shouldn't just change them and train. That's the thing you shouldn't do. You should only change things that are de-risked. This is a word I really like, de-risking. It's basically testing that every change brings performance gains, because you shouldn't change something if it hurts performance. You should definitely not change something and be like, it's gonna work and train with this, because usually that only brings bad surprises, unless you're really lucky. So de-risking brings the notion of ablations, and I'm gonna spend a couple of slides talking about ablations because I think they're really important. So an ablation is basically an experiment, which is small scale, where you change one thing or more in the architecture, and you train the model on a couple of tokens, and then you measure the effects of this change. So you basically have two models, one without the change, one with the change, and you train both on the same conditions, and then you compare the performance, you evaluate both, and you see, does this change bring performance gains? If it does, then you keep it. So when I say performance gains, it should either improve the performance on the benchmarks or maybe just give you inference speed up without hurting the benchmarks. So I think these are the two reasons to adopt a change. Either it brings performance gains on the evaluation benchmarks, or it brings you an inference speed up or like training speed up without hurting the benchmarks too much. And so ablations are small scale, so they should be fast to run, because you don't want to train, say I want to train SmolLM on like 11 trillion tokens. I'm not going to do 11 trillion tokens each time to test a change. I'm going to do a much smaller experiment, and it should be reliable enough that it will give me a signal, and I will trust that this experiment will actually reflect what will happen when the model is trained longer. And there's some scaling laws that show that there are some results that will extrapolate when you train longer. So this is what we do in ablations, and that's why every big model starts with a small ablation, like literally. So to do your ablations and also your training run, you first need to choose a training framework. So this is the framework that you will use for ablation, and you should also keep it for the main run. And for pre-training, there's multiple frameworks like Megatron LM, DeepSpeed, Torch Titan, and Nanotron. I think they're all good options, especially if you just want to train a dense model. And then there's a trade-off that comes depending on your experience. For example, Megatron LM, it's really advanced, but it's also a big code base. It can be harder to debug or like navigate. Although it's really much easier today with AI agents. You can ask Cloud Code to navigate it for you. So we should probably update this table. But yeah, you can choose from these frameworks depending on like if they adopt the architecture you want, or if you're at ease with it. And once you have a training framework, you need to choose a model size and training tokens for your ablation. Because now you know the architecture you want to train and also the model size. But for the ablation, as I said, they are small scale. So for example, here for SmolLM, I gave you our ablation setup. It's a 3B model trained on 100 billion tokens. So whenever we had a new data we wanted to test or new architecture change, we basically trained this 3B model on 100 billion tokens, and we compared the results. If you look at the Kimi K2 paper, which was a 1 trillion parameters model, which was MOE with 32B active, their ablation model was much smaller. It had only 500 million active parameters. So this is what we do for architecture ablations. You can either keep your model size if it's not very large, like we did with SmolLM, but train on less tokens. Or if your model is very large, you can train a smaller model on less tokens, but use the same architecture. One thing to remember is that like for data ablations, it's usually better to do it at the target model scale, just because the small models can sometimes be sensitive or not have enough capacity to, for example, inject many languages. But if you train a large model on this multilingual data set, it will be fine because it is large. So remember that with ablations, you just need like a small scale setup, but it should be enough to get signal. Then after you have good model size and training tokens, you should choose a set of evaluations, because the goal for the ablation is to basically train a small model and figure out if the change helps or not. How do you know if it helps or not if you don't evaluate it? So that's when we come to evaluations. And evals are actually harder than you would think, because they need to satisfy 4 criteria for them to be good evals. The first one is monotonicity. So this model, you're going to train it on, for example, 100 billion tokens, and you should evaluate checkpoints intermediately, and the performance should improve as you train longer. So this is what I mean with monotonic. The score should improve as the model trains longer. The second thing you should have in your evals is low noise. For example, if you run the same experiment with a different seed, you should get very similar results. If the scores really change, then this is a bad eval. And there's so many evals which are like that. I remember when we started SmolLM and Fine Web Ablations, the first thing we did was like look through like 30 evaluation benchmarks and filter them down to just 10, because many of them were like really noisy or not, there was no monotonicity. You would train a model and the curves were like this. So the model was not improving. You should have a smooth curve that goes up. The third criteria you should have is above random. Because some tasks, like if the model is just giving you random predictions, then you shouldn't evaluate on it. And here I have a curve, and this is like MMLU. It's a benchmark which we use a lot in LLM training. It tests knowledge. It has questions about like history, math, physics. And usually the question is like, you have a question, for example, what is gravity? And the model has 4 answers, A, B, C, D, and only one of them is correct. So it has to make a prediction, 1 out of 4. So the random performance is 25%. And for this MMLU benchmark, you can ask the question in 2 different ways. Either you give the model the question and you give it the 4 options in the prompt, and then it has to give you the letter of the correct answer. So A or B or C or D. For example, what is the capital of Paris? A, Vienna, B, Paris. It should give you B. And the second way you can ask this MMLU question is by letting the model give you the full answer. So for example, in the second format, you should expect it to say Paris, not just B. And there's a very interesting thing when training small models is that like they're really, really bad at one of the 2 formats. It's the format where you ask it to give you the letter. For some reason, they can't make the link that this letter, which appeared before the prompt, is the one I should answer. And if you ask it to tell you Paris, it will say Paris. But if you say A, Vienna, and B, Paris, it will probably say A, just because it can't make this link. And we found that this is a capability that emerges later in training. So here, the curve I gave you, like the dark blue, this is the format where we expect the model to give us the answer, so B. And you can see that until 5 trillion tokens, this is a lot of compute, 5 trillion tokens. The model was 25%, it was random on this format. But on the other format where we were asking us to give the full letter of the capital, which was Paris, it was above like almost 40%. So the model knew the answer, but it just didn't know that it should give you the letter. And so here, when we evaluate on MMLU, it's important that we don't use this format, which is random. We should use the formats that the model knows how to answer, which is a bit easier. So this is just to give you an example of like one benchmark, depending on the way you ask the model how to answer it, can give you very different results. And later in training, for some reason, the model starts to know what like letters it should answer, and the performance goes up. It becomes even better than the first formulation. And the 4th criteria for having a good benchmark is ranking consistent. If, for example, dataset A is better than dataset B when you start training, that should still be the case when you're like 100 billion tokens away after training. So the ranking should be consistent. So these are good criteria for testing if a benchmark is good or not. You can take it, train a model, see if it improves. You can train the same model with a different seed, see if the results change, and measure the variance. So now that we have covered ablations and model architectures, I'm still going to show you some other things that we cover in the playbook regarding the architecture choices. Here are some visuals that you have in the playbook. For example, one that explains what is rope, which is basically the rope interpolation that we use in the positional encodings. There's another visual to explain what is intra-document masking versus causal masking. And then we have another one to explain in other advanced attention mechanisms. So if you're interested, you can just go to the playbook. They're all really detailed. And for each one of these, we actually run experiments and we test them and we show you which one works best. So for example, here we have a section where we compare different attention mechanisms. If you remember, I mentioned that like for attention, like when we do attention, you can choose either multi-query attention or multi-head attention. It means whether in your transformer, do you keep all the heads or do you just keep a subset of the heads, and then we compare them. Why do we want to do this? Because when you remove some of them, the model has less parameters, so the inference is faster. And there's research that shows that like attention mechanisms like GQA actually give you the same performance as like the one where you keep all the heads, so multi-head attention. And you can see this here, for example, in the loss, lower is better. So the blue and the green one give you the same loss as the purple one, which is the multi-head attention one. So we have the loss for each change, and we also have the evaluations. So these are our evaluation benchmarks. You can see that they're quite smooth, they go up, maybe except for Bueno Grande, which is a bit more noisy than the rest. But basically for every architecture change that we explain, we also run an experiment and we share the code for it and give the results. So for SmolLM, this is what we actually did. We wanted to train a 3B model because we wanted the model that was on device. In the previous family, SmolLM 2, we had trained much smaller models, which were like between 100 million parameters and 1 billion parameters. For this one, we wanted the model that was just like slightly larger, but still small enough that it could run on phones. So we went for 3B. And to do that, as I said, we chose a dense model because we were memory constrained. And also we had a tight deadline for training this. So we didn't want to explore a lot MOEs. So we looked for a baseline, which was good, which was in this case Quinn 2.5 3B baseline. And then we changed the tokenizer to Llama 3.21B's tokenizer. Because it was better on the languages we cared about, which were English and other European languages. Then we changed the attention to GQA, and we changed the positional encodings to NOPE, and we kept Adam Optimizer. So now that we have answered the what, hopefully you have an idea of like how to choose the model architecture. How do you actually train this model? So the first thing to answer the how is data curation. I think data is like the biggest leverage one has when training models. I think that if you take just like a standard transformer and train it on a really good data set, it's very likely gonna beat like the best architecture on a mediocre data set. And the first question when we talk to answer when we talk about data is like, how long should you train your model? So to know how long you should train your model, usually people use the scaling laws. These are laws that tell you how to allocate your compute budget. For example, let's say you have 50 GPUs for 2 months. Which model size should you train and how long should you train it? Because if you train it longer, then you need to make it smaller because your compute budget is fixed. But if you make the model larger, then you need to train on less data because you're going to need more compute to train a larger model. So these scaling laws basically are laws that tell you how to allocate your budget between model size and data size. So in 2022, we had some laws that told us if you double your model size, you also should also double your data size to use your compute budget efficiently. But then in 2023, people kind of stopped respecting these scaling laws, and they took small models and they trained them really long. So for example, Llama had a 7B model trained on 1 trillion tokens, which at the time was very surprising because the 7B models, according to the Chinchilla scaling laws, it should be trained just like on a few 100 billion tokens, not a trillion. But then in 2024, they took it even further, an 8B model trained on 15 trillion tokens. And Llama 3 was so much better than Llama 1. And this just came from training longer and also a better data set. So models really don't saturate. So if you have the compute and you're willing to pay like an overhead, it's better to train a small model for very long than to actually train a large one. Because the training cost is like a one-time cost, but inference is an all-time cost. Whenever you send the query to the model, you pay something. And this is why even big labs are thinking of how can we train smaller models better. This is the whole reason we have mixtures of experts. This is also the reason we have quantization and things like that, because the inference cost can be really huge. So it's better to pay a small cost in training and not be optimal, even according to the Chinchilla scaling laws. But then in inference, you have a smaller model, which is like nicer because it doesn't require as much compute to run inference on. So the current trend is to basically fix model size and overtrain. Fix model size and train as long as you can. This is what we did for SmolLM 3. We fixed a 3B size, and then we knew that we had 300 GPUs for 1 month, and then we trained for 11 trillion tokens. Now the art of data curation, which like often really looks like this. You just mix things and you hope they will work. But when you publish it in the paper, like I mixed this data set because it was the best one. But then behind the scenes, they were just experiments, ablations. And the art of data curation is basically finding good data sets for the domains you care about. For us, we wanted a model that was good on English and 5 other languages, and code and math. So for each of these domains, we did literature overview to check which of the public data sets are the best on these. And when we didn't find a data set that was good enough, we made a data set on our own. So some of these data sets like FindWeb.edu, FindMath, and StackEdu are data sets made by our team. Also because sadly, all the big labs, they release the models, but none of them release the data sets because that's what gives them their competitive edge, and they don't want to give that to everyone. And also because of legal reasons, if you don't respect the copyright on some data sets, can be really problematic. I mean, Anthropic has many lawsuits because of that, although they didn't disclose the details. So data sets, there's not that many labs that publish them, maybe except for NVIDIA, us, and Allal AI. And then once you have good data sets, you should also know how to mix them, because some of these domains are kind of conflicting, especially when it comes to multilinguality. Like if you train a model just on English, it will obviously be good at English, but then if you want to add more languages, they might come at the expense of English. So you need to have a trade-off, like how much are you willing to pay in one domain to kind of support another domain. Just because, for example, that compute cost, you need to allocate it differently between your domains compared to if you were to train just on one. So there's two methods to figure out how to mix these data sets. There are some methods that try to do it automatically, like Doremi and Rolos. It's like an algorithm. It tries to optimize and find like the optimal weight to give to each data set. For example, 80% for English, 10% for multilingual, and 10% for code. Or you could try to do ablations, like experiments, where you basically change the ratios each time and see which ratio works best. And this is usually more reliable. These automatic methods, they don't always work. So we did that. We found that like if we trained on 12% multilingual and the rest was between English, math, and code, that worked well and didn't hurt the performance on English, which we cared about more. But then if someone cared about another language, they could do that for the other language. And for ablations, you could either do them from scratch or you do them during the training. You basically train the model on one mixture, and then you take an intermediate checkpoint, and you just decay the learning rate, and you change the data mixture. So we have the details for this in the playbook. So when you train the model, there was a time where you have one data set, and you keep that data set for the whole training. You don't change the data set while the model is training. But that's not the case today. People do what we call multi-stage training, where you basically start training with the data mixture, and at some point you change it, and then you can change it again. So for us, we did that. We changed it twice. This is for two reasons, because there's research that shows that if you have a very high quality data set that is small, it's better to introduce it at the end of training rather than at the beginning. Because if you do it at the beginning, because it's small, it's gonna get diluted, or you're gonna repeat it too much, and the repetition can start to hurt if you do it, for example, beyond 5 epochs. So for some small, high-quality datasets that we had that were mostly synthetic, we kept them for the end. Same for math. Like, if you train the model like on a high math ratio since the beginning, it usually doesn't work well because it's something that you need to first know some basic English before being able to do math. So it kind of makes sense. So we start with a low math ratio, but then as the model gets better in general English, we increase the math ratio. And for code, there's some research that shows that like, if you include code, it also helps the model on like general reasoning. Not sure why, but like it's important to have code, maybe because the model reasons to know how to predict the next code block, and it also translates to English reasoning. The model somehow gets smarter. So for code, we already introduced it at a high ratio since the beginning, and we also increased the ratio towards the end. So this is the stages of SmolLM training, and we had a long context extension at the end. This is the performance of the final base model. I think I already shared this, but you basically can see how it performs compared to some other models. These are all open models, but they were open in the model weights, but not in the data side or the training details or the code. So this is for the base one. I have another one for the instruct. So we talked about data curation to get you to how to train this model. So the data curation is the how part for performance. How do I get good performance? It's usually data. And infrastructure, this is a very important part, but nobody talks about it until it breaks. This is like a real training ranks that we had, like you wake up and you're like, everything failed. And if this happens often, it's very counterproductive because even if you spend a lot of time like on the latest architecture, which is supposed to be the fastest to train, and then you launch a training, it keeps failing. Each time you need a couple of hours to restart it, then it was pointless, your whole optimization. So you need a really reliable infrastructure to execute the run in the most efficient way. No infra, no training. In the playbook, we kind of cover the infra really in detail. We explain what is a GPU, how do GPUs communicate between them, because this knowledge is usually just in ML infra engineers. Even for us, like we had one person that was good at infra, and like whenever we had questions, we would go to that person. But at some point, we were like, it would be nice if we understood actually how this works. It would make us also better engineers, and also in terms of thinking about the architecture, how things get optimized and run in experiments. So in the playbook, we explain in detail what GPUs are, that it's how GPUs compute matrices is important. This is like the theoretical throughput, but also how long data takes to move from one GPU to another is as important. So these are things that we cover here. We talk about like GPU level, node level, and then multi-node level, how do nodes communicate between them. And for each of them, we run experiments on our cluster, and we show you how can you profile this on your own clusters to find the bottlenecks and speed up your trainings. So when we talk about infrastructure, usually the people who are doing like the research and training, we just focus on this, like we want the latest GPUs, and we want like throughput optimization. So we take like the best framework, for example, Megatron LLM, that reports really good throughput, and we think that's infra, that's enough. But that's not really enough. This also matters. You should have good cluster interconnect. You should test that when you get a cluster. You should also have like a good storage mechanism. I'm gonna tell you some anecdotes later about how important storage is. You should also have a good node monitoring, because when you started training on a lot of nodes, for example, for us, it was, I think, 48 nodes, and each of the nodes had 8 GPUs. So there was a good chance that things could go wrong, like maybe GPU throttling. Sometimes the temperature would increase on a GPU, and when that happens, the speed goes down. So you should have a monitoring system so that if an issue like that happens, you detect it early, and you go either change the node or fix it so we don't lose time during training. Sometimes you can also have some errors which are silent, and they could affect the computation that is happening on those GPUs, so it could affect the performance. So it's important that you really monitor the nodes that are used for trainings to avoid this kind of silent failures, and also being able to handle these infra failures automatically. For example, one thing that can happen is like a GPU goes down, but if that goes down, and then you need to come back manually and specify another GPU and then resume, it makes you lose a lot of time, especially if it happens often. So for example, for us, like we had a spare GPU, so if an issue happened, the job would crash, but it would resume automatically from the spare node. So we wouldn't need to do a manual intervention, especially because these failures usually happen on the weekend or at night, like the worst times possible. So it's good if you didn't need to have someone awake to kind of resume and fix the issue. Yeah, and you also need good automation and minimal babysitting. If you need to babysit the run, which we did in our early runs, I remember when I joined Hugging Face like 3 years ago, we had to monitor the run and like do the evals ourselves every 50 billion tokens to check that it was going well. But now everything is automated, especially evals. Like this is the biggest time saver. If you can automate the evaluation so that as the model is training, it is also getting evaluated on the 6 benchmarks that I showed. We had like an automatic mechanism for that. So we just needed to check to see how the model was going. We didn't need to do that ourselves. So for the SmolLM infra, it was 48 nodes for 30 days for the pre-training. This is the parallelism setup. We had TP2 because it's tensor parallelism. It means that like you shard the model weights onto GPUs because it doesn't fit on one. And then we had data parallelism. And when we wanted to start the run, like we had everything set, the architecture, the data, it was really good compared to all the other data sets. And then we started the run on 48 nodes. And this is the throughput curve. So basically the throughput is like the training speed. How many tokens is the model processing per second per GPU? So you want it to be as high as you can. And as you can see in the beginning, it was like 14K, which was really good. But then it started dropping, and dropping is bad. It means like it's going to zero, as if the GPUs are idle. They're not doing anything. And we were worried with these drops, and then we had this even worse drop where it dropped to like 8K and it stayed there. So this throughput was bad. And like we did all the experiments before, and we've never had a throughput like this. It was working fine. And it turned out it was due to 3 reasons. 2 of them were because of the infra. This is why I insist on the importance of having good infra. We have good infra, it's just that sometimes things can go wrong. The first one was like a thermal throttling. Basically, some GPUs were aging, and they had a bad cooling mechanism, so the temperature would go up, and this would make the speed of the training drop. So this happened, but this was not really what caused this. An issue we had was storage. So we have a storage mechanism called Weka, which allows you to have a lot of storage. It's, I think, almost 200 terabytes. And it was not filled. But the way the system works is that it's a keep hot mechanism. It only keeps as hot, like the data that you are going to use, and it evicts the data that is called that you haven't used in a long time. It sends it to S3. And when you query this called data and you want to use it, it is going to be there. It's just that you need to query it from S3 first. And at one point, somehow we managed to fill the 200 terabytes, and the model needed to query cold data. And this is what happened here. Like, there was some cold data that was queried, and it made the throughput drop. And this was very bad. I mean, you shouldn't be bottlenecked by storage when you have like the best GPUs. So what we did is that we changed the storage mechanism. And the third reason, which was like, we changed the storage and we still had those throughput drops. It was so annoying because we had fixed everything we could fix. And to debug this, we tried to go back to the experiments we had where everything worked fine. These were the ablations. And the only difference was that the ablations were using a small number of steps because we were training just on 100 billion tokens. And this one was using a big number of steps because this was our 11 trillion tokens. It was very weird. Like, why does changing the number of steps make you have throughput drops? Turned out it was like a data loader bug. I mean, data loaders are the worst, like debugging them and everything. I have nightmares about it. But basically, we were using a data loader, which was building one big index, and the index depended on the number of steps. So because we had this huge number of steps, the index was really large, and it was causing these drops. So we just changed the whole data loader to one that was used by Megatron, and then the throughput was fine. But just fixing this, I mean, it took 5 days. All the optimizations we did for the throughput, they saved us like 1 day. I was like, what was the point for that? It is always the case. The best case scenario is get 1 day. So everything I showed you until now is basically just preparation for your real training marathon. So the real fun begins. Everything is fixed. The throughput was fine. We had the architecture and the data. And this is my colleague, Ellie, who shared on our Slack that SmolLM 3 was training, the loss was going down. We were all happy for, I think, 48 hours. And then this was me, like a couple of days later, saying that we stopped the run because we had an issue. And we stopped after 1 trillion tokens, which is not nothing. The reason we stopped the run is because, wait, first, we did a lot of experiments on the 3B model. And each change we did, it was improving on our baseline 3B model. So changing the architecture, we got better performance. Changing the data, we got better performance. But if you remember, I said that we had a SmolLM 2 model, which was another family, and it was smaller. But then when we did the EVAs, the 3B was as good as the 1B model, and it's not like we just doubled the size for nothing. It's because in all the ablations we did, we were just comparing the 3B model to itself, like similar sizes. And when we did the actual run and we compared to the final SmolLM 2 1B that we trained, it was the same performance and didn't make any sense because we doubled the parameters and the data is better. Everything is better. It's supposed to be so much better. And it turned out, after some debugging, the only thing that was different between the two models was tensor parallelism. If you remember, I said that we used TP2 because the model didn't fit in a GPU. But the 1B model was small, so it was fitting on a GPU, and we never tried tensor parallelism. This was in our nanotron library that we developed ourselves. So we were battling and testing it ourselves. And because we didn't train a larger model before, we didn't try this feature. And it had a bug, and it was a very subtle bug. Basically, when you initialize the TP ranks, because you're going to have two, you start the models, you should use different seeds for the initialization, and we're using the same seeds. It meant that the model started from the same initialization, and it had like kind of duplicated weights. So although it was a 3B, it was almost like a 1.5B model. So the fix for this was like a one-line change, like random seed, you just need to change it and put another number. And it made us waste 1 trillion tokens. But it was fine. I think we still caught it early compared to if we trained 11 trillion tokens. So this is the model after the fix. You do see that it's a lot better. It's the green run, and the one we had before was the purple run, and especially on HellaSwag. So that was the pre-training part. I'm also going to cover the post-training a bit, but I'm more of a pre-training person, so I'm sorry for the post-training people. I'm not going to go into the details here, but it's all in the playbook. So for the post-training, it's important because after the pre-training, you have the base model. It can predict the next token. That's very important, but it's not really useful because people want chat assistants. You want to ask them questions and they answer. To get an assistant, you need to do the post-training. So for post-training, you need to do supervised fine-tuning, so SFT. Everybody starts there. And then after the SFT, you can do alignment. Some people now kind of skip the SFT phase and go to the alignment directly, either using RL or just algorithms like DPO. But usually you get a gain by going through SFT before going to these other steps. Again, for post-training, it's very similar to pre-training. You need to choose a training framework. And for post-training, there's even more frameworks than for pre-training. And so the one that we use internally is like TRL, and it's also very adopted in the community. It's developed by Hugging Face. Once you chose your training framework, you also need to choose if you want to do SFT or if you want to do RL or if you want to do both. So our advice is to usually always start with SFT. Like SFT gives you like really most of the performance, and then you can do some alignment on top, for example, with DPO, which works very well and it's very easy to run. There's also GRPO, which is more of an RL algorithm, but usually RL is like kind of tricky to get right. So not everybody does that, and it's also very cost intensive, especially if the model is large. And then again, for evaluations, you need to select good benchmarks, because again, it's very important that you have benchmarks which measure what you want the model to support. So if you're training general assistant, there's already some good benchmarks you could choose from. Here's the list here. But if you're training a model for some new use case, you need to make new evals and benchmarks for that. And really, it's really important that you get the benchmarks right before you start developing the models. Otherwise, you're going to have these experiments and you're going to have no way to know if they're useful or not. So evals are really important and underrated along with ablations. And for evals, you also need to satisfy the same 4 criteria that I shared earlier: monotonicity, low noise, above ranking, and ranking consistent and above random. So the same thing should apply for this. When you train longer, the performance should increase. When you change the seed, there shouldn't be variance, etc. And if I can give you like one more advice for this, it's that make sure to measure the model on everything that you really want it to support, and also make sure to cover all the tasks you want in the SFT or RL phase, because the models generalize, but if you're really training small models, sometimes they don't generalize as well if you don't really show them data for that domain. And also before releasing the models or deploying them, you should really make sure that you tested them well for those things. I'm gonna give you like an anecdote from SmolLM 1. So I think this was 2 years ago. And our team was mostly a pre-training team. We were not really doing post-training. And I think at the time, people were still releasing just base models. Sometimes you wouldn't even release an assistant. And just because like SFT and RL were like very early on. So we had trained like SmolLM 1, which was like small, just a few hundred million parameters. And we're gonna release just the base model, but then we're like, it would be nice if we made it an assistant. But we didn't have that much post-training experience, so we just took one data set, which was really good on paper. I remember it was called Web Instruct, and it was like very good at MMLU, on math, on physics, and everything, and we did the post-training, it worked well. But then we released the model, and we tried it on like questions like explain what is gravity, what is AI, what are the ethical implications, and it was giving really nice answers. And then we did a demo, and people would, like the first question was hi, and the model would be like, the solution to your equation is this. It was so overfitting on the scientific stuff. It didn't know how to answer hi. And then like, I was like, what? I thought that would like, the model would just know how to answer hi. But there wasn't a single question in the data set that showed the model that the answer to hi should be hello, how are you, or stuff like that. There wasn't any like everyday conversations. It was just like questions and answers about math and physics and science. So in the end, we needed to make this data set, which I called everyday conversations, like literally showing the model, hi, you should say, hi, how are you? Who are you? I'm SmolLM, who trained you? By Hugging Face, and stuff like that. But before that, the model was just so bad. It was very humiliating. But yeah, it shows you that you should test the model on things you wanted to know. Otherwise, if you don't cover that, it's not going to magically know it unless it saw that before. Now I think like even in pre-training dataset, these datasets are in the corpus, so the model probably know how to do that. But at the time when we did it, it was not the case. Okay, so we still have some time. For the post-training, this was the steps for SmolLM. We did some mid-training to make it good at reasoning, and then we did SFT, and then we did the DPO, APO, and in a follow-up release, we also did RL with GRPO. And this is the performance of the post-trained model. It's also on the Pareto frontier of the Qwen3 models. So since the playbook was released, which it's been some time, like in October, I don't think there's any big changes in the playbook. It's still very relevant, especially because we focused on this part, not just like what is the best architecture today, but how do you actually choose an architecture? How do you ablations? And I think these things will be relevant for many years. But when we talk about architectures, I think that this year hybrid attention went really mainstream. When we were writing, it was still kind of debated. Same for mixtures of experts. For optimizers, beyond this optimizer, it's becoming also quite popular and used by many models. Also multi-model first. Many models are now not just text only, but multi-model. There's also a lot of mid-training on existing models instead of doing it from scratch. For example, Cursor's Composer 2 model was mid-trained and doing RL on Kimi K2. So then coming to the end of my talk, if you have some key takeaways, it's that training LLMs is messy. If you're really committing to a training run, you should plan for restarts. So you should have some buffer budget for that in case things go wrong. You should also budget for ablations. Ablations can be really costly. For us, I think our training costs, the ablations were half our training costs. So they cost as much as our 1 month training, just because we spent so much time testing many data sets, testing many architecture changes. You don't need to do as many tests as us, but you should budget for the ablations that you plan to do. And the ablations are really important. They make training more reliable and so also predictable. It's not like you're just training the model and praying it will become good. For us, we had a rough idea where it would land. And then small models can punch above their weight if you do good data curation. So you can find the playbook in this link. And thank you for your attention.
Thank you very much, Loubna Ben Allal, for this inspiring keynote. And wow, thank you so much for your, let's say, step-by-step instructions you gave here and you gave with the SmolLM training playbook. Sure. As we have some time left, we have some time left. There is now some time and the right time for questions. And so, everyone is very excited now. And so, as everyone has now some time to think about their questions, I have one starting question for you. One that probably will be interesting for many of the students that are also here. And that's how someone here who is interesting would get an internship at Hugging Face.
Yeah, of course. So usually we have like internship openings around like October for the April of the next year. So that's when we open like a batch of internships, and you can directly like apply on the websites. I think this year we didn't have that many internships, so it's maybe next year there will be some, but they usually start like around April or March. And like they can also be remote or on site. We have an office in Paris and also one in Switzerland and in New York. And we usually value like open source contributions, for example, on GitHub or on Kaggle challenges. But usually the process is like 3 interviews and you just apply directly on the website.
Thank you very much for these tips. Are there any other questions? So where are they? Have to see. Here, at the second row. So.
No microphone. Okay. So I'm interested in the post-training process. What your experiences are with reinforcement learning with human feedback.
Yeah, good question. So I have my colleagues who work on post-training. They have very mixed feelings about RLHF. have one colleague which have been trying to make it work every time, and every time like SFT is just like faster and easier to get it, and like it gets most of the performance. So for many releases, we ended up doing just SFT. So for example, SmolLM 3, it was SFT with APO, but we had some time later, and we did like GRPO. It gave us a lot of performance boosts on math. So I think for domains like math and code, where you kind of have verifiable rewards, it can be very good there. But it's true that it's really tricky and takes more time to get it right. And even after that, like we had, I think, a release recently where they tried to make a model for theorem proving. You can check that, it's on a Hugging Face release. And it was with Allal, and it worked very well. But then they did some SFTs and model merging, and they got the same performance as Allal. And they were like, oh my God, we spent so much time trying to get it to work, and now SFT works. So very mixed feelings about it. But I think for some things that are really advanced math, advanced code, you do need that. And we see that with like all these like releases from the big labs, where you do need that to get really the best performance.
Thanks.
Yeah, you're welcome.
Are there any other questions? Oh, there in the back. And now I think we have a microphone.
Hello, I wanted to ask, how did you start your machine learning career?
Yeah, so I joined Hugging Face almost 4 years ago. Before that, I was doing a master's in deep learning in Paris. And I did an internship at Hugging Face, because usually in France, you have to do an end of studies internship. And it was about coding models. And then after that, I just stayed full time. And yeah, that's how I started my career. You're welcome.
And there has been another question here and one there, I think.
Hi, thanks for the nice talk. I wanted to ask, has your team also had experiences with like training on images or image-based tasks? And where would you say, is there like, are there like some difference in the whole playbook when working and training with images? Or maybe it's hard to say, I'm not sure.
Yeah, so for images, well, we didn't really cover them in this playbook, but we do train vision models. There's a model called SmolVLM. It's trained on top of SmolLM, and it also has its own papers and documentation. But yeah, I mean, there's some things that apply from here. For example, regarding data curation and evaluations and ablation, it's always the same criteria. And for example, we had to develop our own data set for vision, which was called Fine Vision, just because many of the existing data sets had some issues, for example, with how text and the images are overlaid, and also the quality of the images, and supporting some tasks other than OCR and stuff like that. So things like data curation and the evaluation benchmarks also apply. I think from what I hear from my colleagues that like maybe vision is a bit less mature compared to natural language. For example, there isn't one library for pre-training that people agree on, like Megatron LM, like we do. And also for evals, there isn't like one harness for evals. So I think there is more room for improvements there. But you can check the small VLM work if you're interested.
Perfect, thanks.
Yeah.
There has been another question here, yeah.
Hello, thank you for this amazing talk. I wanted just to ask, first of all, I don't know how many people here have access to 384 GPUs, but still interested in the pre-training. Have you tried things which are not just filling in the word, but things, I don't know, like checking two sentences and to see if they are one follow the other, or any other different training methods other than the masked words?
Yeah, so for us, since we wanted like a generative language model, usually most people use the next token prediction objective with the transformer. It's the one that works the best for generative use case. And also since we went with the standard transformer, it's the one that made sense for generative task. But if we wanted to cover maybe other things like classification or stuff like that, we could have tried other objectives. But no, we only tried this one here. I hope that answers your question.
So are there any other questions? Yeah, here in the front.
Hello. Have you got any experience with time series data? Because the context can get really long, and I read that if the context is really long, you have the mid problem. I forgot the word for that. If the context is really long, the LLM can't interpret anymore what to do with it.
Yeah, so I haven't tried time series personally, but it's true that like long context is something that's important. Usually, like even some models claim that they support, I don't know, 1 million context length, but it's true that like if you do feed it 1 million, it's going to be very bad at recalling the ones that are in the beginning. So you need really good evals that measure how good the model is and what is the real context length. So for that, you need, for example, if you're interested in existing models, there are some benchmarks for measuring long context that are better than others. For example, needle in a haystack, that's a very easy benchmark, not very reliable. There are some that like ruler or helmet, which we use that give like better signal and really tell you what is the true long context. And there's some techniques to get good long context for the models. For example, like we did some changes to the architecture, like using Nope, that really improved. Also did intra-document masking. So there are some things you can change the architecture that will help you have good long context later. But from time series, I have heard that people are trying to make transformers work. I think there's one model for transformers which is popular, but a lot of people still do to like the standard transformer methods like RVMA and stuff like that, just because it's faster and it works better. So I think transformers for time series are still maybe early. But if you're interested in long context, I think the choice of the architecture changes matters for that, and also for the evals you use.
Okay, thank you.
Yeah.
And I think there has been another question in the middle.
Thank you very much for the really nice keynote. I've probably an unpopular question now. It's regarding energy consumption. And one question is, did you track the energy consumption during the training or the different training phases that you had? And how did it guide or restrict certain ideas that you had in your daily life, or kind of ideas that you had for your training and development?
Yeah, that's a good question. It's one of the reasons we are developing small models, because they cost less in the inference and also consume less energy. It's one of the motivations for on-device models. So for us, we did measure the carbon consumption, and we reported this in the paper. You can find information about that. But it's like, for us, you have the choice between like training a large model and it will cost you more in the training and maybe train it less. But then when you release every time once someone uses it, it's going to consume more. So by training a small model, although we trained longer, so it did consume like more energy than if it would have been trained less. We managed to get a small model that is really good by sacrificing this cost in the training, so that everybody that uses it in the inference doesn't have to go through the same costs. So I think like small on-device models were motivated by also having models that consume less. It's one of the reasons we developed these models.
Thanks.
You're welcome.
So I think there will be one question. We have time for one question left, and in advance, maybe you're here afterwards at the break.
Yeah,
Still. Yeah, so we will take one question now and the rest then at the break in person, if that's fine for you. Thank you. So the last question, please.
Thanks for the presentation. Kind of linked to his question, where do you see this going in the future? So we have on one side these very big companies pushing frontier models that are bigger and bigger, and on the other side these very small LMs, but then Google released these Gemma 4 that are the performance is pretty similar or top 3 performant. Do you think the future is local LLMs that are this small, or is it relying on these very, very huge frontier models, also for agentic tasks or, et cetera, et cetera?
Yeah, I think that's a very good question. I think the future is mixed, where you're going to have both. It depends on the tasks you want to do. There's many tasks where you really don't need a frontier model. So many queries where a small model will be enough. So that applies to individuals, but also companies. And then there's many use cases where the company actually needs private hosting for security and privacy reasons. For example, for finance or health, they can't use like front proprietary models. So they need a model that they can host themselves. And because they need to host it themselves, it shouldn't be too large. Otherwise, it will consume too much and it will be hard to host and to use. So I think small models will still exist, although of course, there will be a gap compared to large models because there are some things that only emerge with scale. That's why also proprietary models will be there. And also the user experience. For example, if someone doesn't really have experience hosting, it will be hard for them to host a model, even if the open models that is small is as good as the large one. So I think there's trade-offs, but I think in the future, both models will exist. And even when you think of like frontier models, for example, Code or like Codex, in many of the queries they actually call small models, for example, for summarizing some of the tasks, for doing retrieval. So it's not just one big system that does all the tasks, it's a mix of things. So even in the frontier labs, they have a mix of big and large models, because for them it's also more cost efficient. So I do think that the future will be a mix of both. Yeah.
Thank you.
Sure.
Thank you, Loubna Ben Allal, for this inspiring keynote and answering all the questions. As I've said before, if there are any questions left, she will be there also at the break and you can talk to her in person. And before you leave the stage, I think Sebastian has a little appreciation from the
Thank
USTP
you.
for you.
It's very nice. Thanks.